As promised, we're going to go through a couple examples in 6.3 that we did not get to in class, but I just want to remind you of the most important thing, specifically this blue boxed statement, that the area under any curve is the sum of an infinite amount of rectangles with an area of delta x times f of x sub k. The change in x is the width of the rectangle. X sub k is going to be the x value at which f of x, which is a y value, which is the height of the rectangle. We can also write it as the integral from a to b of some function with respect to x. So let's practice this notation. We are looking at example, we're going to skip this one because we don't need it anymore. But we are going to look at example 3. So this is the last example on the page that starts 6.3 Riemann sums. And it asks us to set up a definite integral that would calculate the area of the region below. So I want to do two things here to figure out my integrals. I need a lower bound and an upper bound. So for this first one, I see that we're starting at 0. Notice the scaling is 1, 2, 3, 4, 5. So I know that my integral goes from 0 to 5. I have my bounds. And the question is, what is my function here? And it's this line, which is the line y equals 3. So my f of x, we could say, is also just 3. This is the integral from 0 to 5 of 3 with respect to x. And in this case, you guys can find this area, right? A rectangle with a base of 5 and a height of 3 would have an area of 15. In our second one, we see, again, the scaling is 1. So 1, 2, 3, 4, negative 4 to positive 4. Now the question is, what is this function? Hopefully you can say, well, I know it's an absolute value function. I know it's an absolute value function that is opening down. It has a slope of 1, and it's been moved up 4. So f of x is equal to the opposite of the absolute value of x plus 4, which means that's what we are taking the integral of, always with respect to x, dx. That's kind of like our delta x there. And that's it. Now, could we find the area of this triangle? Yes, we definitely could, right? The base is 8, the height is 4, 1/2 times 4 times 8 would be 16. And that's your answer. Even though they didn't ask us to do that, it just said set up the definite integral. Let's look at some more examples. Sketch and shade the region whose area is given by the definite integral. Use geometry to find the area. First one we have is the function 2x plus 5 bounded from negative 2 to 0. So I start by drawing that line. It is a line that starts at 5. The slope is positive 2, so down 2 over 1, down 2 over 1. And notice this is the area in question, because we're looking from negative 2 to 1. Now, of course, you could draw the entire line. It doesn't necessarily matter, but we really only need that red area. How do I find this area? Well, I see that it is a trapezoid. So 1/2 base 1, which is 1, plus base 2, which is 5, times the height, which is 2. I get an area of 6. So the integral from negative 2 to 0 of 2x plus 5 with respect to x is 6. For our next one, I look at this function, the square root of 9 minus x squared. And maybe you remember this, maybe you don't, but I feel like this is a circle centered at the origin, because it would be x, well, hold on, let me go back. Technically, okay, I know this is a circle, but if you want proof of sorts, here's our function. I square both sides, add x squared to the other side, and now I see that I have a circle centered at the origin with a radius of 3. But because I took the square root, which remember, when we take a square root, we're getting positive or negative, and I'm only left with the positive version, I know that this is just going to be the top half of a circle. And they want us to find the area under this curve from -3 to 3, so we are looking at this shaded region. Because it is a circle with a radius of 3, and I want to find half of the circle to find the area, I want 1/2 pi times my radius squared, so the area would be 9 pi over 2. Last but not least, we have the integral from -1 to 1 of 1 minus the absolute value of x. I'm going to start for myself to reorder this. Negative absolute value of x plus 1, then that's very similar to the last example we did where it's an absolute value function that is reflected down and moves up 1. So I know it's going to look like this. The area I'm interested in is from -1 to 1. Now it's just the area of a triangle. 1/2 base, which is 2, times height, which is 1, for a grand total area of 1. One small thing that I did not mention in class, and I'll try and say this again in class, about integrals is that it gives the signed area. So if I find this area, okay, let's say this is A, B, C, and D. The integral from A to B of this function with respect to x, let's say it has an area of 4. And then if I find this area right here, and I'm told that the integral from B to C of this function, let's say it would be -5. I'm just making up the shaded areas. The integral down below the x-axis is negative. It gives us a signed area, takes that into account. And we'll look more with properties of integrals soon, but I did want to point that out because in our next example, we need to use that. So it says, given the graph below, find the solution to each of the following definite integrals. Use the provided graphs to resketch a graph of the function depicted in the integrand. All right, so here's our original function. I don't think they mention it, but we can assume that this is a half circle and then everything else are straight lines. So I'm going to go ahead right away and just find all the areas that I need so that when we go piece by piece, it's a lot easier. I'll start with this circle, has a radius of 2, so the entire circle would be pi times 2 squared, or 4 pi, but this piece, just this half, has an area of 2 pi. Then I look at this little rectangle, excuse me, triangle right here, which has a base of 2, a height of 1, 1/2 base times height gives me an area of 1. If I look at just this little rectangle here, 3 times 1, this has an area of 3. This tiny little triangle, 1/2 base times height gives me an area of 1/2. And last but not least, this triangle over here, base of 2, height of 2, 1/2 base times height gives me an area of 2, but it's negative because it's below the x-axis. So I'm going to write it, I guess I could write it inside there as -2. All right, now let's look at our first example. The first one says the integral from -4 to 0 of negative f of x with respect to x. So first I'm going to start by doing this transformation. The opposite of our function, think about it, remember back to transformations, changing our y values. This is a reflection over the x-axis. So my function actually looks something like that. And they're asking us to find the area under the curve from -4, so that's 1, 2, 3, 4, -4 to 0. So we're looking at this area right here. I'm going to use my drawing above. I see that it's half of the circle. So 1/2 of the 2 pi plus this area of 1, but because it's all below the x-axis, I'm going to make that all negative. And so I would have negative, and depending on how you want to write this, I am going to write this as negative pi, negative pi plus 1. Our next function is the absolute value of f of x. So think about that. Any y values that we have of this function that are negative are actually going to be positive. So all of these stay. This is exactly the same, but this down here gets reflected above the x-axis. So we are asked to find the area under the curve from 2 to 6. So I'm going to shade that in. 1, 2 to 6, which is all the way at the end here. And I know that this, I'm going to look up here. So 2, this is 1 and 1/2, so 1.5 plus this area of 2, 3.5. For these next two, I am going to remind you of the transformation and then let you try and figure it out, what area we're doing. This first is f of x plus 2. Ooh, we got to think back to our transformations. Plus 2 is going to move it to the left 2. So each piece, let's see, is going to be 1, 2, 2 to the left. Okay, let's see if I can draw that. And they want us to find the area from -2 to +1. This is the area we're looking for. Pause the video, calculate it. I got 3. And then for this one, we are moving our function up 2. So it's going to look something like this. Oops, I made that too far to the left, but it doesn't actually matter because we're only looking from 0 to 3. Notice, because we moved the function up, this area goes all the way down to that piece. So what is that area? Pause the video, calculate it. I got an area of 9. So that is all the examples in 6.3, and you will have a notes video on 6.4 at some point soon.